Okay, so last week, actually last week, lecture, in the last lecture, we were discussing like energy transfer dynamics in molecules, like how the energy transfer happens in molecules, like polyatomic molecules. And we are also discussing the rate theories, like to compute the rate constant of the reaction, chemical reaction. So we are discussing transition state theory, which is the popular one, then RRKM theory, RRK theory, etc. So both transition state theory and the RRKM theory are the statistical rate theories. So what do we mean by statistical? Statistical means, these theories don't care about the dynamics, because to compute the rate constant here, we don't need to know explicitly how the dynamics is happening, like how the atoms are moving and chemical reactions is happening. We don't need to know that. We just need to know the features, some features of potential energy surface, like reactant well around the transition state region and the product well, etc. So the main assumption of these theories are instantaneous IVR. That means, so here the main assumption is instantaneous IVR, means the IVR is the intramolecular vibrational energy redistribution. So it is basically intramolecular vibrational energy redistribution. So this means, let's say, if we excite one mode or let's say water. So if I excite this one wage mode by putting or by dumping energy using the external laser field, then how the energy transfer is happening, like from this mode to this mode, or from stretch mode to bending mode, etc. So how this energy transfer is happening, this term is called the intramolecular vibrational energy redistribution. So the TST, both TST and the RRKM theory, or in general the statistical rate theories, assume that the dynamics of IVR or time scale of IVR is instantaneous. That means the time scale of energy redistribution is very fast compared to the typical reaction time scale. So IVR time scale is very fast compared to any typical reaction time scale. Reaction time scale, I mean, because let's say water to, let's say, dissociation, let's say H plus OH. So this is a type of chemical reaction. So the time scale of this reaction is slow compared to the energy redistribution time scale. So this is the meaning of instantaneous IVR, and this is the origin of the statisticality. So by assuming that, we are kind of neglecting the dynamics, that explicit dynamics that is happening from like energy distribution dynamics, like how the energy is distributing or is transferring from this mode to this mode, or any stretch mode to bending mode. We are kind of ignoring that. We are kind of bypassing this process. So that's why we call these processes, we call these rate theories or statistical rate theories. Now, in most cases, in polyatomic molecules, or most chemical reactions, this is not in general true. Like some cases, IVR time scale is fast compared to any typical reaction time scale. But in most of the cases, we can see experimentally also, we can observe that the IVR time scale is not too fast compared to the any reaction time scale. So sometimes what can happen is that, let's say any polyatomic molecule, let's say CHCl3. This is a polyatomic molecule. And if I dump a particular amount of energy into the CH bond, CH local stretch bond, let's say, then sometimes can happen that this energy can transfer from this CH mode to this CCl mode. But then this CCl mode to another CCl mode, it is not, the energy transfer is not happening too fast. It can happen. So that means this energy transfer dynamics is deviating from the statisticality, because the energy can get localized into a particular bond and it cannot redistribute between all possible vibrational modes fast, very fast. So that is the deviation from statisticality. And we call this non-statistical dynamics. Now, to understand this non-statistical dynamics or the deviation from statistics, yeah.
So the which one transfer higher energy, CH mod to CL or CL mod to CH?
No, here I'm just, it's a typical example, not accurate example. I'm just saying that it can happen. The energy cannot transfer from one mode to another mode very fast. I'm using CHCl3 as a typical example, not the accurate one. I don't know the energy transfer dynamics of CHCl3, so I'm just using it as an example.
Okay.
Yeah. So I'm saying that if I dump a certain amount of energy into a particular mode, sometimes it might happen that instead of redistributing that amount of energy into all possible vibrational modes, sometimes it might happen that that energy corresponding to that particular mode can get localized into another vibrational mode, and then from that vibrational mode, the energy cannot turn. Energy transfer is not happening. Sometimes it might happen. So that is the situation where we call the deviation from statisticality. So we term this non-statistical dynamics. So in this non-statistical dynamics, so dynamics is very important here. To understand this, we have to compute, or we have to understand the dynamics, how the energy transfer is happening between different possible vibrational modes, like one mode to another mode. This is the typical example is this. It's a theoretical example. It's in the left side. It's some n coupled oscillator. So this is one oscillator. Let's say this is pendulum. One oscillator. This is second oscillator, third, fourth, fifth, sixth, like this. Now these pendulums or oscillators are coupled with a nonlinear coupling. Nonlinear coupling. So linear coupling is the harmonic oscillator type coupling. That's a KX type coupling, right? So nonlinear coupling means some higher order terms are also there. Yeah. So these oscillators are coupled nonlinearly, in nonlinear fashion. Now this is the famous model of Fermi-Pasta-Ulam. We also call that PU model. And many decades ago, they actually studied this model theoretically. So what they did, they actually dump a certain amount of energy, or they excite a particular pendulum, let's say fifth pendulum here. They excite this pendulum. Now they are actually observing or studying theoretically or computationally how the energy from this oscillator or pendulum is getting transferred into another oscillators, like let's say 6, 4, 3, 2, 1, etc. So they actually studied the energy transfer dynamics of different oscillators. Now, what they observe is that the energy from the fifth mode, or let's say for the fifth mode, can get localized. Let's say fifth mode to fourth mode, it is getting transferred very fast. Then fourth mode, the energy can get localized here, or it can spend certain amount of time here in this oscillator, depending upon the coupling strength and coupling type, the form of the coupling, etc. So what is happening here is that, so energy cannot transfer, or energy is not getting transferred very fast from the fifth mode to all possible vibrational modes, right? So that is the clear observation of deviation of statisticality. Now, this is a linear oscillator type. Only just n oscillator is coupled in a nonlinear fashion. But so if you just translate these theoretical studies to a real molecule, So real molecule also different local mode, different stretch mode, bend mode, CH, CN, CO, etc. Different possible modes are there. And all these modes are, we can assume that all these modes are oscillator. We can model all these local modes as an oscillator. So similarly, all these CH, CN, CO modes are coupled intramolecularly in a nonlinear fashion. So these are all coupling. Now, similar to this observation, if you just excite one particular mode, let's say for a protein or for a amide, you just excite this CO mode. Okay. Now you are just studying the energy, how this certain amount of energy from the CO mode is getting transferred from the CO mode to, let's say, CN mode, NH mode, or other helical modes like low frequency mode, like the let's say alpha helix or beta seat, like all the low frequency modes. How the energy transfer is happening from this local mode to other modes. So this study is very complex. This understanding of the energy transfer dynamics in polyatomic molecules is very complex. So yeah, that is the study of non-statisticality. And in the real life example is that experimentally, let's say there is the ozonolysis study, let's say from a ether. If you sorry, in a ozonolysis study, so from a reactant molecule, let's say the potential energy curve look like this. Like there is an intermediate. This is intermediate, and from this intermediate, the two possible products can form. Like this is product 1, let's say, and this is product 2, let's say. So this is the common intermediate, and common intermediate only two product channel can open. You can imagine from the intermediate, two product channel is opening with different transition state, and different barrier height, right? So you actually studied this typical potential energy curve in BSc or MSc. So now here the non-statisticality, what is the origin of non-statisticality? Sometimes it can happen that in the intermediate, when the reactant molecules are forming complex and forming the intermediate, sometimes it can happen that energy transfer means when these two reactant molecules are colliding and forming a particular complex, let's say endo complex or exo complex at the transition state. So forming the complex due to collision or some other things, then so different modes has different energy, right? At the time of forming the complex at the transition state. Now these energy into different modes, let's say this mode, this mode, this mode, or this mode. So then energy can relax, like energy from one mode to another, energy can transfer from one mode to another, and like this. So energy will relax, and then this transition state complex will relax to get back to a intermediate form, right? So sometimes it can happen that the energy transfer is happening very fast. Let's say energy transfer in this complex, transition state complex, is very fast. Then that means the transition state complex is thermalizing. Like thermalizing very fast means the energy transfer is happening instantaneously. So all the possible vibrational modes are getting equal amount of energy, I'm saying that. Okay. There is no localization. All the possible vibrational modes are sharing equal amount of energy. Then we say that the intermediate is thermalized, properly thermalized, and equilibrated with the external bath or solvent like this. Then the intermediate is situated here. Now from this intermediate, two product channel can open, like A channel and B channel. And the product ratio, like the extent of formation of product A and product B, this product ratio, we can determine thermodynamically, right? Like the product ratio will depend on the transition state barrier, like transition state barrier for the A channel and transition state barrier for the E channel. We know that this is, we call this thermodynamically controlled product. Okay, just a second. So we call this thermodynamically controlled product, right? Now, let's say, let's imagine a different condition. Now, let's say the energy from this mode to this mode. So this energy transfer at the transition state is not happening very fast. Let's say at some mode, some vibrational mode, a certain amount of energy can get localized, or it can spend a certain amount of time in that vibrational mode compared to the reaction time scale I'm saying. Now the situation is the intermediate is not properly thermalized or properly equilibrated with the solvent or channel bath, right? Because here it can happen that this OO mode is getting higher energy and this CO mode is getting lower energy, let's say. So it is not properly thermalized now. So now the intermediate is not situated here. It can situated here, there, here, like this. Different configurations are possible. But depending upon the content of energy into some particular vibrational mode, the product ratio will vary now, right? So if we experimentally we observe similar kind of reactions. There are many examples of this, of non-statisticality. So this is the deviation of statisticality when energy can get localized into a particular vibrational mode, and the intermediate cannot properly equilibrate with the external thermal bath or solvent molecules. Then, depending upon the content of energy into a particular vibrational mode, the product ratio will vary. Now, let's imagine if we just control, or if we systematically dump a certain amount of energy into a particular vibrational mode of our choice, of our interest. So let's talk about a simple molecule, formaldehyde. Let's take this example, right? So if I now imagine that if I can systematically dump a certain amount of energy into this CH mode, and if I can control the energy transfer dynamics, if I can control the energy transfer from CH mode to CO mode, then CH mode to another CH mode, let's imagine that I can control that. I have all the power to control the energy transfer dynamics. Then I can control the chemical reaction itself, right? So that is called site selective or mode selective chemistry. Now, it has the huge potential. Like if I can control the energy transfer dynamics of certain vibrational mode, then I can effectively control the fate of any chemical reaction. That means we can systematically produce our desired product, like L conformation compared to R conformation, like this. So that is called the mode selective or site selective chemistry. Okay, now before going into the details of energy transfer dynamics, so here I actually giving you a overview of slow overview of different terminology or different concept to understand this topic. Like, then if you listen any talk related to this, then you can instantaneously grasp all the points or all the contents he or she trying to talk about. So it is very important to know these terminologies. Okay, first one is the phase space, right? So we know there are two types of space you can imagine, like configuration space and the phase space, right? The configuration space is just the coordinate space, Q1, Q2, Q3, like Qn for n degree of freedom system, right? This is just the configuration space, and the phase space is the 2n dimensional phase space with both coordinates and momentum, right? So basically it is Q1, Q2, Q3, both Qn and P1. Then P1, P2, P3, both coordinates and the conjugate momentum are there. So it is the 2n dimensional space. Now in the phase space, let's say for a 1 degree of freedom system, so Hamiltonian will be like p squared divided by 2m plus, let's say for one harmonic oscillator. So it will be half m omega square x square, right? Now the Hamiltonian is integrable. That means the integrability of any Hamiltonian means for in general, for n degree of freedom system, you have to have n constant of motion. Constant of motion means, sorry, constant of motion means the in variable or in quantities will not change over time. Okay, so that is the constant of motion. So for n degree of freedom system, you have to have n constant of motion, and let's say these constant of motion are f1, f2, f3 like this, and then both these has to be the independent constant of motion. That means the Poisson bracket of f1, fi, and fj should equal to delta ij. Okay. So this should be the independent constant of motion. Then we can say that that corresponding the Hamiltonian, n degree of freedom Hamiltonian is integrable Hamiltonian. So here, let's say for 1 degree of freedom system, the Hamiltonian is this is kinetic energy p square by 2m plus for one, let's say harmonic oscillator system, the potential energy is half m omega square x square. Now here the Hamiltonian is constant of the motion, right? Because we know that the energy is constant here. This is one harmonic oscillator, so energy is constant. So Hamiltonian is basically the total energy. So Hamiltonian is constant of motion. So 1 degree of freedom, oh God. So 1 degree of freedom and 1 constant of motion. So this is an integrable Hamiltonian. Now the dynamics of integrable Hamiltonian in the phase space, we call it the 1 Tori. Tori means, so basically it is, so in general for n degree of freedom system, n degree of freedom integrable Hamiltonian, n degree of freedom integrable Hamiltonian, the phase space looks like n parameter family of n Tori. I will discuss the Tori. What do we mean by Tori? Okay. Now let's say for two uncoupled harmonic oscillators. So Hamiltonian will be H1 plus H2, right? So H1 will be p square by 2m plus half m omega squared x1 square. H2 will be p1 p2 square by 2m plus half m omega squared x2 square, right? Now here H1 is constant of motion, H2 is separately constant of the motion because the harmonic oscillator are uncoupled. They are not talking to each other and they are independent. So basically, so in these cases, two harmonic oscillator, uncoupled harmonic oscillator, 2 degree of freedom system, 2 constant of motion, so it is an integrable Hamiltonian. In this case also, the phase space will look like 2 Tori. I will discuss the meaning of Tori. So basically, from this Hamiltonian, like in general, H equal to some momentum square by 2m plus V of function of Q. Potential energy is a function of Q. So this is in general Hamiltonian, right? Now we can transform this Hamiltonian from PQ variable to a new kind of variable. It's kind of coordinate transformation, like going from Cartesian coordinate to polar coordinate, like this. So we can transform this PQ Hamiltonian into PQ variable to J theta variable, let's say. Here, the J is action and theta is angle. Okay, so we can transform PQ phase-space variable to a action angle variable. Okay, J theta. Now this transformation is called the canonical transformation. So there are different conditions to satisfy the canonical transformation. I am not going to go into the details here. So basically, action means now. So now, if we just J H as a function of J theta, if you just express this new Hamiltonian H, let's say H bar as a function of J theta, then for an integrable case, the Hamiltonian will only function of J, right? So if this is the old Hamiltonian in PQ variable expressed in the PQ variable, and then you transform this Hamiltonian into two different variable J and theta. Okay, let me just check if internet is stable or not. Okay. Now, if you transform this Hamiltonian into J and theta, and then if you express this old Hamiltonian into a new Hamiltonian, which is a function of J and theta, then for an integrable case, the Hamiltonian will be only a function of action J. It will be independent of theta. Now, if you express this Hamilton's equation of motion in the new variable, so theta dot will be del H del J, and J dot will be minus del H del theta, right? This is Hamilton's equation of motion. Okay. Now J dot will be minus del H del theta. Now this new Hamiltonian is independent of theta, right? So J dot will be 0 in this case because H bar is independent of theta. So in the new variable, J is a constant of motion. So if you take an initial J, initial action value, now this action value will be constant forever with time. Only theta will vary, angle will vary. Now, if you transform this into a Tori concept, what do you mean by the n parameter family n Tori? So let's say for 1 degree of freedom system, the dynamics of the phase space will look like 1 Tori. That means just a circle. That means only one J and one theta is there, and J is constant and theta is varying. So this radius of this circle is J and theta is varying from 0 to 2 pi. So 1 Tori means equivalent to circle. Okay. So Tori T1, we express this in the mathematical sense, T1. So T1 is equivalent to S. Circle, we express this S. T1 will be equivalent to S. Now for 2 degree of freedom system, we have said that the phase space will look like 2 Tori.
Subhadip, just one small clarification that you told that 1 degrees of freedom means one constant of motion. Okay. For integrable system.
Yes.
But here the new Hamiltonian is a constant of motion already.
Yes.
H bar, and also J is another constant of motion.
No, it is not independent, right? H.
Okay, those.
Yeah, those are dependent because H is only a function of J. So
okay, no.
J
Okay. Their Poisson bracket is not.
Yeah.
Okay. Okay.
So that, I forgot that integrability theorem that I was just talking about. So that is called the Liouville-Arnold integrability theorem. So now for 2 degree of system, the phase space will look like 2 Tori. 2 Tori means 2 parameter family of 2 Tori. Here are 2 parameters are J1 and J2, right? No, sorry, parameters are θ1 and θ2 because those are varying from 0 to 2 pi, θ1 and θ2. Now, what, how it is how does it look like? 2 tori. So 2 tori means a donut. So in the American donut, just so here. So this is a picture of 2 tori or donut, let's say. So from a center, you can imagine 2 circles here, right? One circle is going like this, one circle is going like this, and another circle is going like this. At each point of this first circle, you can imagine another circle. Okay. Like this. So this is another circle, each point, and once another circle is going like this. Okay. So this is the example of 2 tori. So there are two variables, two parameters, θ1 and θ2. So for a bigger circle, for this bigger circle, from center to this to the radius is, let's say, J1, and from smaller circle from center to the radius is J2. So J1 and J2 are constant for a particular energy value. J1 and J2 is constant. Now for different energy, the shape of the tori will look like, it will be a smaller tori or bigger tori depending upon the value of J1 and J2. You can imagine that, right? Because J1 and J2 are just the radius of these circles. Now θ1 and θ2 means θ1 is varying, let's say, from 0 to 2 pi like this, and θ2 is varying from 0 to 2 pi like this. You can imagine that, right? So basically 2 tori or T2 means S1 times a direct product of S1 in the mathematical sense. Okay. That means circle, and from each point of that circle, you have to imagine another circle. Okay, S1 times S1. Similarly, 3 tori T3 will be S1 times S1 times S1. Now, so mathematically, S1 times S1 or T2 in general is not equivalent to a sphere. Okay, because a sphere and tori are topologically different, because there is a hole in the middle of a tori here, right? There is a hole, and sphere there is no hole. So you cannot deform a sphere into a tori. So these two are topologically different. So that's why T2 not equivalent to sphere. So what I'm trying to tell is that for an n degree of freedom integrable Hamiltonian, the phase space will look like n parameter family of n tori. So in most cases, we generally consider about the 2 degree of freedom system. So for a 2 degree of freedom system, phase space, what is the dimension of the phase space? 4, right? 4-dimensional phase space, because P1, P2, Q1, Q2. So phase space dimension is 4. And if the energy is constant, obviously the total energy is constant. So the energy hypersurface in the phase space will be 3. Because 4 minus 1, because actual phase space dimension is 4. And now if we constant the energy, if we fix a particular energy, then energy hypersurface will be 4 minus 1 will be 3. Like this. So now this 3-dimensional energy hypersurface is filled with this 2 tori or donut. You can imagine that. Okay. This is filled with 2 tori. Now the concept of surface of section. Now, how do we visualize the dynamics? So in a molecule or in any cases, the dynamics is happening in its own way, right? So in the 3-dimensional energy let's say if we fix a particular energy, H equal to E1. Now at this energy hypersurface, the trajectory is moving. Now, how do we visualize these dynamics? So the pointer actually gave this solution, how to visualize the dynamics in a 4-dimensional phase space or 3-dimensional energy hypersurface. So if we 3-dimensional surface, so energy surface is 3-dimensional, right? So if we just fix a plane, if we consider a plane here, so this is 3-dimensional. This is energy hypersurface. Now, if we consider a plane here, now if you start from this point, if you start from this point, now dynamics is happening. So with time, these points will move, right? Now this will move, and let's say after certain amount of time or certain time step, this point or this trajectory will again cross this plane at a different point, right? Then when the trajectory is crossing this plane, this our choice of plane, we are noting these points, this cross intersecting points. Again, this trajectory will move, and after certain amount of time step, this will cross at a different point. So we just write down, or we just note down these points, and we can plot these points, Q1, P1, or Q2, P2, like this. Then we can easily visualize, like it is the kind of cross section. So we can visualize the whole dynamics into a cross section of the whole phase space, 3-dimensional phase space. Okay, it's just in the Tori concept, if you fix one theta, so if you fix, let's say for this theta, this big circle, if you fix theta equal to 0, let's say this is theta equal to 0, theta 1 equal to 0, right? So here you consider a plane here, this plane, like, sorry, theta equal to 0, you can imagine that I'm not drawing it correctly. So theta equal to 0, and you consider a plane here. Now, whenever a trajectory will cross this plane, we are noting this down. Okay, so it can cross again and again here at a same point, or it can cross at a different points at each time, right? So this is like a surface of section. Okay, now the resonance condition. Same for 2-dimensional harmonic oscillator. 2-dimensional uncoupled harmonic oscillator. Okay. Now the phase space will be 2 tori. 2 tori, J1, J2, theta 1, theta 2. Now there are 2 frequency here, like for each oscillator, let's say omega 1 and omega 2. So if the ratio of omega 1 and omega 2 is rational, let's say 1, 2, 3, 4, 5, 6, like this, then we call this is a periodic orbit, right? Periodic orbit means if I start at this point, just messing it up. So this, let's say this is theta equal to 0 plane. And if I start from this point, this trajectory will move around and will intersect at same point. So this, let's say this is omega 1 by omega 2 equal to 1 by 1, 1:1, let's say. So it will evolve around the big circle one time, or it will evolve around the small circle also one time. So 1:1 means like this. So it is the periodic orbit. Another, let's say it is 3/2. 3/2 means, let's say omega 1 is 3 times and omega 2 is 2 times, means the trajectory will evolve around the bigger circle 3 times and around the smaller circles 2 times, like this. And the periodic orbit will, or rational, if the frequency ratio are rational, then the trajectory will cross same point. We intersect this plane at the same point. But if it is irrational, if omega 1 by omega 2 is an irrational constant, then if you start from this point, then trajectory will move around, then it will go closer to this point, infinitesimally closer to this point, but not exactly this point, because you can approximate infinitesimally closely for a rational value to a for an irrational value to a rational value, right? Similarly, for a irrational ratio, if you start from this point, then trajectory will move around and it will go close to this point, but not exactly this point. So with time, it will fill the whole circle. Okay. So this is a closed orbit, and we call it invariant curve. So there are different names for this. For irrational ratio, so trajectory will go to every points on this circle. So it will form a closed orbit like this. Okay. So these are the resonance conditions. Resonance means omega-1 and omega-2 will be some rational value, or it can have irrational value also. We call this quasi-periodic orbit, or if it is rational, then we call this periodic orbit. Now this omega-1 and omega-2 is constant. Sorry, it is the fixed value, right? Because this is harmonic oscillator. The omega-1 and omega-2 will not depend upon energy. But for a nonlinear oscillator, or Morse oscillator, let's say, the frequency omega-1 or omega-2 will depend upon energy, right? If you increase energy, if you know this, so if you increase energy, this energy gap will decrease eventually. That means the omega frequency of this oscillator will decrease if you increase energy. If you go from here to here, then the frequency will decrease, and eventually at the dissociation energy, the frequency of this oscillator will be equal to 0. You know this. So for nonlinear oscillator case, let's say for the Morse case, this initial omega-1 and omega-2 will depend upon energy. So it will be a function of energy, let's say J. J means energy. Action is typically corresponds to the energy. Is a function of J. Now, consider it. Okay, before that. So this is the phase space look like for a not uncoupled harmonic oscillator. All the closed curve, okay, at different energy. So at smaller energy, the ellipse will be smaller. You know that at higher energy, the ellipse will be higher, like this, because J1 and J2 value will be increasing. So that's why the all will be closed curve. Okay. Now for a coupled oscillator, now if you couple these two oscillators with a, let's say, lambda x square y term, where lambda is the coupling strength, and if you increase the coupling, then sometimes these closed curve, or we call the invariant curve, will start to overlap with each other. Okay, so these resonance, these orbits will start to overlap with each other, and the overlap region. There is an expression for the overlap region or overlap criteria, which you know, the Chirikov Russian mathematician. So Chirikov overlap criterion. Okay. Now it will depend upon the coupling strength. So basically, it will depend overlap region will depend root over of lambda exponential times the let's say chi times order of the resonance. Order of resonance means, like, if omega-1 by omega-2 equal to 1:1, then order of resonance is 1 + 1 = 2. If it is in general n1 by n2, then order of resonance will be n1 + n2. Okay, like this. So it is proportional to root over of coupling strength. So if we increase the coupling strength, then the overlap region will increase, and basically the more orbits will overlap with each other, and it will deform like this. So these two curves are basically 1:1 curve. Okay, so if you are observing or you are visualizing at one section, let's say this is P1 and this is Q1, and there will be another section like P2 and Q2, right? So you will observe that for this curve, there will be similar type of curve in the other section. So we call this 1:1 curve, resonance orbit. Then these are invariant curve. I'm not going into the details here. So then these random points, this purple region are called the chaos or chaotic region. So I will discuss the chaos later. Chaos means the random points. Those are the random points. So basically the main concept, I'm just trying to get into that, with the increase of coupling strength, like if we couple different oscillators with a nonlinear coupling, here the coupling is nonlinear, right? Nonlinear coupling, then different periodic or invariant curve, periodic orbit or invariant curve will starts to overlap with each other and form different types of interesting region, resonance region, chaotic region, invariant. These are called cam curve, cam orbit, or Kolmogorov-Arnold-Moser orbit. So different types of structures starts to emerge in the phase space if we couple different oscillators nonlinear in a nonlinear fashion. And with the increase of coupling strength and with the increase of energy, these structures will vary. Okay. So basically the main concept is in real molecules. So in real molecule, there are different local modes, and those modes are coupled to each other in a nonlinear fashion at a certain energy. If you just visualize their phase space, you will see these different types of structures, resonance structures, different types of resonance, like 1:1, 1:3, and in n-dimensional case, it can be more complex, and chaotic region like this. Okay. So basically, this is the real example. So it is a 2 degree of freedom surface reflection for a 2 degree of freedom system. So here I'm adding the omega c and energy. Okay. Now just focus on this plot. So this purple one, this is P and Q section, and this is PC and XC section. Two different sections. Now for the corresponding to this purple curve, you see that purple curve here, right? And this is 1 corresponding to 1. So that means this purple region is 1:1 resonance region. Okay. These are chaotic points, gray points are chaotic points. And you also see these two curves. So here there are 2, and here there is also 2. These are 2:2 resonance region like this. Okay, so there are different types of resonance region you can easily visualize by visualizing their phase-based structures. Now, these phase-based structures actually contribute significantly to the energy transfer dynamics. How? Because these are basically the resonance, like between two oscillators. So let's say two oscillator, one oscillator. So two oscillator, one oscillator, and two oscillator. If they are in resonance, like N1 by N2, let's say their frequency ratio is N1 by N2. That means the energy. So one oscillator will lose N1 quanta, and another oscillator will gain N2 quanta, right? So basically, this resonance channel will facilitate the energy transfer between these two oscillators. Okay, so that is the importance of different resonance. Now, in general, for a 3-dimensional or multi-dimensional case, so there will be like omega 1 by omega 2 will be something like this. And this omega 2 by omega 3 will be, let's say this is N1 by N2, this is N2 by N3, like this. For the general multi-dimensional or 3-dimensional multi-dimensional case, for N greater than or equal to 3. Okay. Now for a particular energy hypersurface, so let's say this is an energy hypersurface, constant energy. Okay. Now different resonance region, let's say this resonance, this omega 2 minus 2 omega 5 plus omega 8 equal to 0. 3 modes are interacting with each other or are in resonance in this particular fashion. So there will be a curve like this. there for another resonance, there will be another curve. Let's say this is omega 3 equal to omega 9. So this is 1:1 resonance between 3 and 9 mode. So there will be another curve like this. So all this resonance curve will be on this energy hypersurface. And now they can intersect with each other for n equal to 3, n greater than equal to 3. All these resonance curves, let's say these curves, all these resonance curves can intersect with each other, and they can overlap with each other with the increase of coupling strength, and they can form resonance junction. Okay. Now let's say these two curves are intersecting at this point. Let's say this curve corresponds to the 1:1 resonance between one oscillator or first oscillator and the second oscillator. Just imagine that. And this curve corresponds to the, let's say, 1:1 resonance between the second oscillator and the third oscillator. So this is corresponds to the first and second, and this is second and third. That means at this junction, the energy transfer channel can vary, right? Because let's say energy transfer first happening along this resonance region, 1:1 first and second oscillator, and here energy transfer was happening between the second and third oscillator. Now at this point, all three oscillators are coming together in resonance, right? At this junction. So junction plays a very important role in scrambling the energy between different possible vibrational modes, which are present at the junction. Okay. Now in real life example also, in different crossing or different junction, you can change the routes. Here also, on the energy hypersurface, there are many different roads, and different roads can form a junction at certain points. At those junctions, energy transfer routes also can change. Okay. So this junction actually helps to facilitate energy transfer between different possible vibrational modes. Just checking the internet connection. Yeah.
So if just before going further, so and to understand better way means it seems too fast for me that in the Tori that you cut it a Poincare cross section and theta equal to 0. That
yes.
That visualization is much easier.
Yeah.
And you explained here that for different if omega 1 by omega 2 is irrational, okay, if they are rational, those visualization much easier. But in the next example,
yes,
the real harmonic oscillator. Harmonic oscillator means coupled harmonic oscillator and uncoupled harmonic oscillator.
Yeah.
Yes. Here, suppose left side is a Poincare cross section for a particular energy. Yes. And at a particular, you cut the surface at particular energy and at particular value of what is the other constant?
No, just a particular energy. I'm just constraining a particular energy, and then I'm just visualizing the section.
Okay. Just there you just fixed particular theta, and all others variable are just you check at that particular value.
Yeah, you can imagine like in the phase space variable like px xy variable also. So just fix this H0. Okay, this is the total energy. Yes. Then you sample px py xy according to this total energy. Okay. Now you just do the dynamics, and you can select a particular section, particular plane. Let's say the section is Q2 equal to 0 and P2 greater than 0. Let's say. Okay. So now you just put the Q2 equal to 0 plane, and you just, when the trajectory will cross this Q2 equal to 0 plane and with momentum P2 greater than 0, then you note down Q1 and P1 points. Okay.
Okay. Means
Okay.
this surface is Q2 equal to 0, means
Surface is Q2 equal to 0.
Q2
So
equal to
basically
0.
these
Okay.
plots are, let's say here P1 and here Q1. Like
Okay.
this.
Okay. And in the right side, due to the nonlinear resonance, means those each constant of is this J constant, like in Tori, those are not remaining constant in the right part.
No, H is actually constant in the right part. The total Hamiltonian is this.
H is constant.
H is constant.
H is constant.
Now this uncoupled periodic orbit or uncoupled this curve.
With respect to this J or J value with respect to the H0, this unperturbed Hamiltonian, those are not constant of motion now. Means if we understand, if we means right part is that we want to understand this coupled oscillator in terms of this uncoupled picture, just like orbital.
So those are not in the Tori picture. For the uncoupled case, both J1 and J2 are constant of the motion. Okay.
That's okay.
That's why you are getting this whole curve. But in the coupled cases, this Tori will starts to deform. Okay. Then different Tori comes into the picture and they will overlap with each other and form this kind of structures actually.
Because we are just trying to see what are the uncoupled in terms of uncoupled Tori. We are trying to interact. It means bases are the uncoupled. Bases are the uncoupled.
Bases are the uncoupled.
Yes. Just like in our DFT, we always our reference is independent orbital.
Yes.
Okay.
Okay. So
why these resonance islands are identical?
No, identical means let's say two oscillators are in resonance. It's a 1:1 resonance. So basically, in one section you will get one orbit or one point or one region. In another section also you should see one region or one point, right? Because these regions or these orbits or these structures are coming from this picture. Like if you see the trajectory moving, like let's say 1:1. So let's say first you fix this plane, θ1 equal to 0. So 1:1 means trajectory will move around and intersect once. Okay, that means trajectory will move around the bigger circle one time and around the smaller circle also one time. So okay, now let's say, so that's why in both sections, so if you just consider θ2 equal to 0 plane, that means you fix this plane, this bigger circle plane, and you see if you see the intersecting points, you also see one point or one intersection. Now, if the oscillators are in resonance like 2:1, 2:3, that means the trajectory will move around the bigger circle 2 times and around the smaller circle, let's say 3 times. Okay, so in different section, you will see different region. Like in one section, you will see 2 regions or 2 orbit. Another section, you will see 3 regions. Okay. Got it?
But this coupling is not symmetric.
No, symmetry. Why symmetry is coming here? The coupling is not symmetry. I'm saying that the resonance, particular form of the resonance, let's say 2:3. Okay. That means one trajectory will move this bigger Tori 2 times. 2 times. Okay. And in the smaller circle 3 times. In one time scale. Okay. Means okay. If I start from this point, then trajectory at the end, it has to come to this point, right? And before coming to this point, the bigger circle, around the bigger circle, the trajectory will move 2 times like this. And around the smaller circle, the trajectory will move 3 times. I'm not drawing it correctly. You can imagine that, okay? So that's why you get different regions, like corresponding to different resonance, different particular resonance. You can visualize different regions in different section. Okay. Now, like this, so this is like, so this is 1:1, these curves. That's why in both section you are seeing one region. Okay, now this is also 2:2. These regions also 2:2. So that's why in both section you are seeing 2:2. If it is, let's say, 2:3, then in one section you will get 2 regions, in another section you will get 3 regions, like this. Okay, so yeah. So just to complete this, like basically I'm not telling any details here. There are many topics I wanted to cover. Okay, so basically, what do you mean by chaos? So chaos is basically the sensitivity to initial conditions. So if I start from different initial conditions, let's say if I start 2 different trajectories from nearby initial conditions, after certain time, these 2 trajectory will diverge. Okay. This is chaos means. Chaos means the dynamics of different initial conditions is very sensitive to the initial points. If I start very close, if I start the trajectory from very close points also, then after certain times, you cannot predict those trajectories. Those trajectories will diverge from each other. Okay. So this is chaos means. So there are 2 types of chaos, the deterministic chaos and stochastic chaos. Deterministic means the chaos is generated from the deterministic equation of motion. Like, you know the analytical expression of equation of motion. Still, you cannot predict their future. That is deterministic chaos. But in the stochastic chaos, you have some stochastic term or disorder. Okay. Now the first, you probably know the term butterfly effect. So basically, the butterfly effect originates from the chaos theory. So we know our weather is in general chaotic, right? So we cannot predict the future. We cannot forecast weather accurately. So weather is in general chaotic. So there are many differential equations we have to solve with different parameters to forecast our weather. Now, in earlier days, there was a model of weather forecasting, and some scientist was actually solving numerically that model to forecast weather. Now he actually observed that the variation of air pressure due to a flying butterfly, let's say in South America, can cause or was causing a tornado in the North America. So बटरफ्लाई की वजह से जो एयर वेरिएशन हो रहा है साउथ अमेरिका में, वो एक टॉर्नेडो को ला सकते हैं नॉर्थ अमेरिका में. Okay, so he was observing that with that model. So that's why this butterfly effect term is there.
Air variation by butterfly means
the butterfly is flying, right?
Yes, okay.
That local air variation, air pressure variation.
Mm-hmm.
So basically, they are solving different differential equation.
Okay.
Differential equation with many parameters like air pressure.
Okay, at this small length scale, it is visible. It is connected to that.
Basically, why they were observing that? They were observing because at small decimal points also, like from 15 to 16 decimal places also, if you change one decimal, if you change, let's say 0.0000001 point or one air pressure, and another air pressure, let's say 0.00001 2 or 101, let's say this. So if you put these 2 points also, after certain time, so let's say आज शाम को हम ये 2 points कंप्यूटर में सॉल्व करने के लिए दिया है एज ए इनपुट टू एयर प्रेशर, देन कल प्रेडिक्ट करने के लिए बोला है. सो कल मशीन वेदर प्रेडिक्ट कर रहे हैं कि let's say this is the pressure for in North America, or this is the pressure for the South America due to butterfly. So with the machine predict कर रहे हैं कि for these points आज नॉर्थ अमेरिका में टॉर्नेडो आ रहा है. मतलब कि ये 2 पॉइंट्स इतना नजदीक है, बट फिर भी कुछ टाइम के बाद डायनामिक सॉल्व करने के बाद ये 2 टाइम एक दूसरे से डाइवर्ज हो रहा है. ठीक है, तो वही कैओस है. मतलब हमें तो वही एक्चुअली हमें बेसिकली कैओस इज बेसिकली सेंसिटिविटी टू इनिशियल कंडीशंस. तो 2 नियरेस्ट इनिशियल कंडीशन भी एक दूसरे से डाइवर्ज कर सकते हैं आफ्टर सर्टेन टाइम. Okay, because the weather is in modern days, there are many parameters, many complex differential equation, coupled differential equation. Due to more computational power, we actually can predict somehow the weather, but weather is in general chaotic. Now chaos can actually we can observe chaos in many example, like different complex dynamics. Let's say for simple equation like z square equal to z square plus c. This is a very simple equation. J is the complex number and c is also a complex number. So if you start with initial j and initial c, and if you just iterate this equation time and time again, then you generate different points. Like these are explicitly chaotic, and there are different sets also, like Mandelbrot set and Julia set in the complex dynamics with the similar type of equation, z square equal to z square plus c. And you can generate this type of beautiful structures here. And these are self similarity. मतलब अगर हम इस स्ट्रक्चर को इस पॉइंट को अगर हम इनफाइनाइटली जूम करें तो हम सेम स्ट्रक्चर्स दिखेगा. जैसे कि फ्रैक्टल्स में होता है, आइस क्रिस्टल में होता है, तो वो सेम, इसको बोलते हैं सेल्फ सिमिलरिटी. Okay, so and there are the many importance of self similarity also. Like you can question yourself the origin of our universe, universality, nature of us, like this, because in tree branches, leaves, blood capillaries, our brain cell, our universal connection, river delta, everywhere you can see these type of similar structures. Okay, the origin of these structures are very similar because they are of the same origin. So you can explain the origin of our universe or origin of different structures, etc., different shapes. So these are very important. Yeah, so I'm just concluding here with the famous Nikola Tesla quote. Thank you. Yeah, if any questions are there, you can ask.
Fractal is also in the structural perspective. Fractal are there, and that I heard. But in the dynamic and in the phase space also, fractal is used. The
concept of fractals are very general in mathematical sense. If the dynamics of the phase space is not integer, or sorry, dynamics of the phase space name, dynamics of the I forgot that. If it is not integer, then these fractals type of shapes will generate actually. I forgot the details.
Fractal dimension I heard a lot.
Yeah, fractal dimension is a non-integer dimension.
Or integer dimension. Means integer means if we just like extensive property. If we increase the scale, the property also scaled that accordingly. L to V, volume, length to volume. This is Q. So first to third dimension. Fractal, if it is in fractal space, then not 3. This is a fractal. This is a factor, non-integer.
3 by 3.5, 3.75 like this. Yeah.
In the phase space also there would be.
No, no, I think it is the dimension of trajectory. I forgot that.
Okay.
Yeah. Fractals are in general self-similar. Because if you zoom infinitely, then you can see similar structures.
Yeah.
Basically, I also wanted to talk about today the Fermi resonance and the spectroscopy, overtone spectroscopy, but I didn't get enough time. Yeah.
Okay. Yeah. Next time. Yeah.
Yeah. Next time. Okay. So, any other questions? And I actually touched upon the last chaos topic because this is my favorite topic, and I just wanted to show those photos or figures because that's the kind of motivation I get from this topic, because you can easily observe these types of structures everywhere in your surroundings.
In the last discussion, you told some similarity with the celestial.
Yeah. Celestial mechanics. Yeah. Okay, so if no other questions, then we can stop. So I have a meeting from 6 p.m.